Welcome to my TED Talk, How to Please All of the People All of the Time. First, I'd like to give my thanks to Denisa and the Math Club for hosting me, giving me this opportunity, as well as to all of you for coming. If you need to leave early, feel free to. Since this is being recorded, you could always check the VOD later and send it out to all your friends. This is a subject I'm fairly passionate about, and this talk I'm really proud of. So hopefully it should be very entertaining and educational for you. We'll start out with a simple situation where we have 100 voters, 64 of them vote orange, whereas that means the 36 of them are wrong. Now, we don't want to call up all 100 voters every time there's some little decision to be made. So instead, we'll get representatives whose job it is to make decisions. We'll have 10 delegates. Now, you can think to yourself, what would be the best way to apportion these 10 delegates among the 64 orange and the 36 wrong? But stop thinking about that because it's not your choice. It's the choice of each individual district. So for example, this top district up here has 6 orange voters and 4 wrong voters. So the orange voters take this district, giving an orange delegate. Continuing on, we see that all of the delegates are orange. So this makes sense. Why would you want a representative that's wrong? Why should people be given a voice if they're just going to use it to say the wrong things? Ironically, though, if they're not given a voice, they'll never shut up about it. So we can redraw the districts. Here we have the same situation, 64 orange and 36 wrong. But now, in this top district, it's 4 orange to 6 wrong. So the wrongs finally get a delegate. In fact, they get 6 out of the 10 delegates, meaning they get to make all of the rules, including how districts are drawn in the future. So how did this happen? How did a minority of voters end up with a majority of the power? Well, when you think about it, all you need to win is a little more than half of the delegates. And each delegate corresponds to a district, so you have to win a little more than half of the districts. In order to win a district, you need a little more than half of the voters in the district. So a little more than half of a little more than half means you can win with a little more than a quarter of votes. This is a well-known technique, perfectly legal, and even given a name. It's called gerrymandering. While in this case it ended up being bad, it's still a nice trick to keep in your back pocket in case the majority is wrong. You can fix everything yourself. It reminds me of an adage by Joseph Stalin. The way he phrased it is a bit different from how it's said these days. More catchy version, it's not the people who vote that count, it's the people who count the votes. For our next example, we'll look at a direct democracy. We have these bears, a grizzly, a panda, and a brown bear, and they're living in a zoo that'll take care of all their worldly desires as long as they can agree what to eat each day. So they take a vote. There's 1 vote for bamboo, 2 votes for salmon, and 0 votes for porridge. So the first day, they have salmon. The second day, they vote again with the same results. So they have salmon again. Third day, more salmon. And so they end up eating salmon all the time. Now, this is an anonymous poll, so we don't know which bear is voting for bamboo, or even if it's the same one each time. But we can imagine they might feel disappointed that bamboo is getting 1/3 of the votes, yet is never served. You'd think maybe it'd be more fair if had bamboo 1/3 of the time. So we can take a page from machine learning as adapted from evolutionary biology and introduce some randomness. It seems here that we're already in the perfect position. Any small change is just going to make things worse. However, calculus students recognize this might just be to our vantage point. If we zoom out, take a global perspective, we see just over the horizon, there might be an even better position that we can get to with a big enough change. So maybe in this situation, some of the bears had never had bamboo before. They've never tried it in a boat. They've never tried it in an overcoat. Once they do try it, they realize, hey, I love this stuff. Not mixing up your options can also itself be dangerous. Like maybe eating salmon all the time is not the most balanced nutrition. This can be exacerbated by a change in environment so that a once viable option no longer is. So, like maybe an increase in mercury has caused the salmon to become poisonous. So the bears decide to change their voting method, where now they write their votes on slips of paper, put them in a hat, draw one at random, and so they end up eating bamboo 1/3 of the time, salmon 2/3 of the time. This is a pretty sweet deal they have going on. Word gets around about it, and a Allosaurus hears and decides to move in. So now, 25% of the time, they're going to eat bear. This is one of the dangers of randomness. Sometimes it can have disastrous results. When you're having multiple concurrent trials, it's not so bad. So, like, a random mutation might cause someone to be born with only half of a lung. But the only person who suffers from that is the one with half a lung, and also everyone that knows them, and also any sympathetic person who hears about it. But the species as a whole marches on indifferently, and in fact, relies on those mutations. There may come a day when a change in atmospheric pressure makes having less lung advantageous. So now they're the ones marching the species on, whereas everyone else is suffering. But sometimes you can't afford a mistake. So, like a random change to the code in a super intelligent robot might suddenly cause the apocalypse. And it's even worse when you only have one trial. We live in a society. One wrong decision could collapse of all our systems, and then we wouldn't have a chance to make further decisions to fix it. Anyway, back to the Allosaurus and the two bears. At the drop of a hat, they've gone back to their old method, but also the Allosaurus has invited over some friends. Also, the smell of a rotting carcass has attracted a group of flies. So now we have 5 dinosaurs who want to eat bear and 4 flies that want to eat actual garbage. So what do the bears do? Well, the grizzly wants to eat salmon. The panda wants to eat bamboo. But at this time, it might be better to prioritize. So they'll rank their preferences from most to least ideal. This is called a preference ranking. We can make this easier for ourselves to read by reversing it so that the candidates are in a constant order, whereas the ranks are what get rearranged. This is called a preference ranking table, and we can use it to include all of the voters. But then we run into another problem with legibility. However, note that all of the theropods have the exact same rankings. So instead of each getting their own column, we can combine them into what is called a voting block, and then denote how many voters have been combined using a number at the top. So hypothetically, if everyone just goes with their favorite, then we'd have 1 vote for salmon, 1 for bamboo, 5 for bear, 4 for trash, and bear wins. But the bears, according to the rankings, would not be so thrilled about this. But really, they had no chance of swaying the election in their favor. Their candidates only got 1 vote each. This is similar to in American politics why they say voting third party is a waste of a ballot. The field is dominated by 2 main candidates who have the only realistic chance of winning. So why bother supporting a candidate that doesn't have enough support to win? It creates a vicious cycle where in order to get more support, the candidate has to already have enough support. So instead of going with their favorites, the bears can look down their rankings and see which of these 2 options do they prefer. And we see garbage. Predicting all this, they could change their vote and make garbage barely win. 1 plus 1 plus 4 equals 6, which beats out the 5. This voting, different from what your true preferences are, is called strategic voting. And it can create a lot of very interesting, very pathological effects. For example, there may come a day where the panda and the grizzly have little babies, and there would be enough of them that if they work together, the Pizzly bears would be able to sway the vote in favor of bamboo. However, bears can't count or talk, so they don't realize they have the numbers advantage, and so they continue to side with the flies. For the flies themselves, they could actually bolster their own side by making their opponents bigger and scarier, say by inviting over a sarlacc that wants to eat and digest bears over the course of 1,000 years. Overall, strategic voting is the sign of a broken system. It turns what should be a good faith decision-making process into just a game to be manipulated by those with the least investment. It can create trash pandas, and it's something to be avoided. So how can we avoid it? We can make use of these preference rankings we've introduced. I'll go into a bit more detail here. First is the core idea. If a candidate A is ranked better than candidate B, then the voter would prefer A to win the election over B. Second, we're going to place some restrictions on how rankings work. Every candidate is given a unique rank from first up to the number of candidates. So, for example, you can't have two favorites. We're going to force Sophie to have a first and a second. Otherwise, it would really be more of a rating than a ranking. You also have to rank everything. Nothing's left unranked, even if the voter knows nothing about the candidate. And if there's only 10 candidates, you're not allowed to take the rankings up to 11th. Finally, the relative ranks of candidates are unaffected by the existence of other candidates. This is a very logical requirement, but might not be so clear just from the description. You might need an example. The problem is that human preferences aren't always so logical. I'm sure everyone has had the situation where they want to go out to get some traditional all-American cuisine with a friend. And so you ask, hamburger, taco, or pizza? And your friend says, let's get the hamburger. And then you realize, wait a second, the pizza place is closed anyway. And so your friend responds, oh yeah, good point. Then let's get tacos. It's not logical, but it happens, yet we're going to ignore it. By the way, I hope you've had dinner because I'm going to keep talking about food. For example, our next example, where we have 26 people are going to have a dinner party and they want to decide what to serve. And the options are steak and beans, steak and corn, steak and potatoes, or fruit salad. We'll look at all the first ranked votes. We see fruit salad wins plurality. Note the phrasing there. It's a plurality, not a majority. A majority means more than 50%. Since there's 26 voters, that means you would have to have at least 14 for it to be a majority. It's like a plurality of Americans live in the city of New York, but that doesn't mean the half of our population is crammed in there. It just means that NYC is bigger than any other individual city. In fact, if we look, it seems that a majority of the guests want to eat steak. They just can't agree on what side to have. This is what's called the spoiler effect, where having multiple similar candidates causes them all to weaken and split up the vote amongst them. I can relate this to a fable, story of a fox and a wolf fighting over prey. The wolf is bigger and stronger, so it scares away the fox and gets the food. But a similar situation, a fox, a wolf, and another wolf. Now, the two wolves fight each other while the fox grabs the food and runs. The spoiler effect is kind of similar. It's another reason why third parties are looked down upon in American politics. Having a strong third party candidate can actually help out their main opposition, since they end up siphoning votes away from the one that they're more aligned with. And we can see here, Steak and Corn came in a close second with 7 votes. So this block of 7 might be feeling kind of bitter towards the other guests for not just sucking it up and voting strategically and allowing them all to dig into that cow. To sum it up, plurality method, pro, it's simple and familiar. Most polls you'll ever see use this method, and everyone knows how to do it. You just pick your favorite. Even if they don't know how to use it, they can learn in an instant. Just pick your favorite. As a con, everything else about the system, it's absolutely terrible. You should never use it. It's not even simple once you get into strategic voting, since now voters have to try to predict what other voters anticipate how other voters are going to vote. It's a complete mess. This mess comes from that split there between a plurality and a majority. You can avoid this by only having 2 candidates. In that case, a plurality is always a majority. In order to get more than your opponent, you have to have more than 50%. There's a give and take where in order for one bar to cross this middle line, the other one has to as well. You can even avoid the case of a tie by having an odd number of voters. However, if you ask a yes or no question to a Zen Buddhist, they may respond with mu, which is less of an answer and more of a rejection of the question itself. So when we take that into account, it does call into question our claims of a majority. 33% of eligible voters is not really a majority. It's just a majority of those who voted. However, this idea itself of having 1v1s is still pretty good, and we can synthesize it into situations where we have multiple candidates by using what are called head-to-head matchups. We'll start with fruit salad since it won the plurality. Now, we're not just looking at the first-ranked blocks anymore. We're going to let all the other voters still have a say, and we'll use their other rankings in order to determine it. For example, in this first block, second is better than fourth, so they'll give their vote to steak and potatoes, whereas third is worse than second, so they'll vote for fruit salad. Once we go through it all, we see steak and potatoes wins a majority against fruit salad, so we can cross fruit salad off the list and move on to other candidates and see that steak and potatoes also manages to take down steak and corn, but it loses to steak and beans. So now all of the candidates have lost except steak and beans. That doesn't mean that steak and beans is the winner though, since this case is only due to the order in which we check the matchups. We still need to give the other candidates their shot against steak and beans. But if we do, we see it beats steak and corn and fruit salad. So steak and beans wins in all of the head-to-head matchups. This makes it what is called a Condorcet winner. Pardon my French. So reviewing this, the Condorcet winner has a compelling claim to being the correct conclusion, considering it wins a majority against every other candidate. And in fact, the fact that it's a different majority each time allows everyone to share in the victory. It's also pretty much immune to strategic voting. It's pretty rare for it to be advantageous to allow one of your worst ranked preferences to win against one you ranked better. As a con, it's a bit more difficult. You have to explain preference rankings, which can be difficult with certain people, especially if they're asking, why we have to go through all this stuff? Why can't I just pick my favorite? But still, preference rankings are a pretty intuitive concept, and I was able to, I hope, succinctly and thoroughly describe them here. So why is such a small con outweighing these incredible pros? to the point where we would ever need any other system of voting? Well, it has to do with the fact that head-to-head matchups are not a complete system. While ties can happen in the plurality method, you're just unlucky if they do. Whereas you have to be fairly lucky in order to get a Condorcet winner. And a system that doesn't give a final answer is not really a system at all. Next, we'll look at a system which makes ties even less common than plurality, and also finally makes use of all of the numbers on our table at once. It's called Borda's method, which is strange that it's named after someone considering it's such an intuitive idea. All we're doing is turning these ranks into points. So for example, we have to remember each column corresponds to more than one voter. So these 2 voters give 1 point each to Steak and Beans. These 3 also give 1 point each, while these 7 give 2 each, and so on. So 2 times 1 plus 3 times 1 plus 7 times 2 plus 6 times 2 plus 8 times 2 gives a total of 47 points. Those in linear algebra might recognize this sum of products and realize we're just doing a matrix multiplication. This fact might inspire you to come up with some more fancy voting methods. But for now, we'll just give 1 point for each rank. But we have to remember, being ranked first is better than being ranked second. So like in golf or in racing, the winner is the one with the smallest number. In this case, it's Steak and Beans. Contrarily, Steak and Corn has the most Borda points, meaning it has the least wide appeal, despite getting the second most votes in plurality. So that really puts egg on the cob of those cornholes. Also, note that Steak and Beans has the fewest number of people who mark it as their favorite, and yet it's never ranked any lower than second. This ties into Borda's method's main pro, which is it favors moderate, agreeable candidates, as opposed to swinging wildly between extreme fringes. It also is resistant against strategic voting. While you can still do it, it's so complicated with so many moving parts and it has such a weak effect that it's often not worth it. But as a con, it's a really complicated system. You still have to use preference rankings, plus it's a lot more strict with them. With head-to-head matchups, you could get away with fudging the requirements a bit, but not as much with Borda's. Plus, it's even complicated just to calculate the winner, especially if you're doing it by hand. It's very time-consuming, easy to make mistakes, even more so as you increase the number of voters and the number of candidates. So far, we've been comparing these methods on these 3 main axes: strategic voting, ease of use, and the characteristics of a winner. But there are other properties we could look at and want from a voting method. For example, non-dictatorship. No one voter decides the election. Usually you'll actually want something stronger where all the voters are treated equally. We also might want universal domain so that anyone can vote in any way they want. Pareto optimality is a no-brainer despite the fun name. If all voters prefer candidate A over candidate B, then candidate B cannot win. So this is like, if one of the options is pizza with a drink, then the winner should not be just pizza. That's strictly worse. Literally everyone will just be asking, where's my drink? How am I supposed to eat this pizza without my drink? Finally, independence from irrelevant alternatives. If A wins an election over B, then adding or removing candidate C should not allow B to win. This is analogous to the final requirement we had of preference rankings. We also saw that this property is violated in plurality, if you recall the story of the fox and the wolves. So what's with this big blank spot up there? Is this where I'm gonna write out the mythic rare system which satisfies all 4 of these conditions? I see a lot of people smiling because they realize it's the opposite. Arrow's impossibility theorem states that no preference ranking-based system satisfies all of these properties. However, note this caveat here, no preference ranking-based. So are there other systems that are not preference ranking-based? Probably the simplest one is the approval method, which is a lot like the plurality method, but you're allowed to have more than one favorite. Each voter gets to vote for or approve of as many candidates as they want, and they can do it any fashion that they want. They could approve of their top three, or they could split it down the middle and approve of exactly half. Or they could just only approve of one candidate. The choice is theirs, and they could even decide to approve everyone, but that has the same effect as approving no one, which is the same as not voting at all. So in a much more literal sense, this is a waste of a ballot. There's also nothing saying blocks have to remain blocks. For example, we have these 8 people with the same rankings, but maybe one of them diverges in terms of approval. Maybe this is a bean boy and he keeps thinking about those beans. So even though he shares the same rankings with everyone else, he gives different approvals. You might also note that his approvals are the same as in this block, despite having different rankings. And so we see that approvals picks up on different things from rankings. So on the one hand, approval would not be able to distinguish between voters A and B. They both dislike hamburgers and tacos, and they like pizza. But ranking can tell the difference since A prefers tacos over hamburgers, even if A still doesn't like them. On the other hand, approval is able to distinguish between A and C, in that C does like tacos. Whereas in terms of ranking, these are the same. Taco is second in both of them. On the gripping hand, neither system can tell the difference between D and C. We can say that D dislikes tacos, but is still willing to tolerate them. This is a facet of the approval system. Voters get to choose their own criteria for approval, which can leave some inconsistency as to what's actually being measured. It's like if you ask people what the best movie is, you're leaving it open to interpretation. So they might think, is it my favorite movie, or is it the movie that has more objective standard of polish? Or maybe it's the movie with the most wide appeal, or the one with the greatest cultural impact, or even just the one that makes the most money. The respondent doesn't know what to make of the question, and you won't know what to make of the answer. Anyway, once we have these approvals, we add them up like before. We have 2 approvals plus 3 more plus 6 plus 1. Remember, the rankings don't matter at all. We can just ignore the numbers entirely. Once again, fruit salad is in the lead. And so it seems that even though in general steak and beans is favored, most people still don't really distinguish that much between it and fruit salad. And just because it's favored doesn't even mean that it's liked at all. So pros of approval method, it's still fairly simple. It's the same as plurality. You just approve of as many as you want. It's also like Borda's method in that it selects a candidate liked by most people. If you want to choose between the two, you can sort of frame it so that Borda's method selects the candidate hated by the fewest people. It also discourages strategic voting. We've already gone over the cons, that approval method misses some of the nuance, and voters may not have the same standards for approval, although those are more of differences than outright negatives, since in some situations you might want voters to be given some freedom. And we also saw approval picks up on some nuance that ranking misses out on. Now let's go back to this discourages strategic voting thing. What do I mean by that? Well, if we look back at our table, we see this column done goofed. They let their least favorite option win. Even though they approve of it, they could have not. And that would allow steak and corn, which is not their favorite, but it's still, according to the ranking, a better option, the victory. In this case, it's less voting strategically and more voting meaningfully, since they had approved anyone anyway. But it still illustrates the way of strategic voting can work differently in an approval method election. Whereas instead of throwing your most preferred candidate under the bus in order to support a more popular candidate, you can throw a popular candidate under the bus in order to support your preferred candidate. But we want to try to avoid everyone doing it, because then Blau snap back to plurality and fruit salad once again the winner. Another thing to keep in mind whenever we're discussing this strategic voting is that we get the luxury of looking at all of this after the fact, after all the votes have been cast, and we can see how everyone's preferences line up. For the voters themselves, there's a fog of war. All they know is how they themselves are going to vote. They're not privy to other people's preferences. So if we look from the point of view of this block, let's say these three know each other enough to know that they have the same preferences. They also know that fruit salad and steak and beans are both very popular. So maybe they could sabotage fruit salad and allow steak and beans the victory. And it turns out they played themselves. They made their least favorite option the winner. This is what I mean when I say approval method discourages strategic voting. To go back to another fable, there's a story of a dog who has a bone, and he's real happy about it. He's walking around and he comes across a beautifully rendered lake. And he gazes into the water and sees in the upside down, there's another dog there with another bone. And he thinks to himself, that blue dog ain't so tough. I could take his bone and then I'd have two. So he looks at the other dog, lets out a terrifying bark. And as he does, the bone falls out of his mouth and into the lake, and he ends up with none. So no bones about it. Greed is a competition against yourself. So this is a non-preference ranking based system. So that means Arrow's impossibility theorem doesn't apply. So why is that not listed as a pro? Well, it turns out that there's a even more general theorem that does apply to the approval method. And while these theorems all have formal proofs, I can still illustrate problems that arise just from a simple example where we have three voters and three candidates. In a plurality election, each of the candidates gets one vote, so there's a three-way tie. In Bordas, they each get 6 points, so there's a three-way tie. In approval, they each get 2 approvals, another three-way tie. How about head-to-head? Well, on the one hand, jam is able to defeat lobster. On the other hand, it loses to pear. And then on the gripping hand, pear loses to lobster. So there's a cycle here where jam beats lobster, which beats pear, which beats jam, and there's an irreconcilable deadlock. No system can give a fair outcome. So in the end, you have to think about the conditions of your vote, what you want to accomplish with it, and review the strengths and the weaknesses of different methods, see how they align with what you want, and choose the option that works best for the situation. And if you do all that, then you can end up pleasing most of the people most of the time. However, that's not the title of the talk, and that's not what I promised you. So what do? Well, I did mention that when there's only 2 options, all of the deterministic methods boil down to the same thing of siding with the majority. So how about that? Well, unfortunately, most things in life aren't just yes or no, this or that, black and white selections. In fact, viewing everything in these terms is related to what psychologists call splitting, which can be a sign of personality disorders like narcissism. In reality, there's usually a third option, which is not a combination of the other two. People are going to want to go for it. Even when there is a true dichotomy, sometimes neither of the options are preferable. Sometimes it's a decision between a giant deuce and a turd sandwich. So, what do? At the end of the day, it seems like there's always going to be someone that's dissatisfied. This is a problem that has haunted philosophers and politicians for ages, but we're mathematicians, so it's our job to solve problems. And this is actually a very easy one. It's the kind of problem you'll encounter many times as you go through your math career. For example, finding a projection in the Jiangsu algebra, finding a normal subgroup of the alternating group on 5 symbols, finding a Clopin subset of the quaternions, solving the differential equation y equals y prime minus y double prime squared plus the fourth derivative of y times the cosine of y times t. Finding an integer solution to a to the 12th plus b to the 12th equals c to the 12th. Finding a natural number that's half the sum of its digits. Or finding a natural number that evenly divides 7. If those hints haven't helped you out yet, I have one more, and it's the fact that the solution is hidden within the very symbol we use to mark a correct answer. I have now solved the human condition. You may applaud me.